which keep, can you put keep notation?
Sorry?
Oh, okay, keep. So Jabot will tell alternative and maybe better pathway to utilize coupling files. So first two talks by Daniel and London did provide universal methodology to compute coupling files. And then we went into master equation approach, which is way quicker, but not always more precise. What Jabot is going to present is different way to utilize these couplings and get potentially more precise information, but it will cost much longer for computing electron dynamics.
Before starting, thank all of you because almost you covered all of my steps. So it will cover kind of repeating all of the steps. Oh. So this is kind of methodology. What do I do? So I just took slide from Dr. Kleiner. So I guess we don't need to go through this one. Just one big thing is we need to calculate. We need to define this basis set based on the adiabatic trajectory in the ground state molecular dynamics. So in the in our methodology we
first previous slide once again. Yes. So where are non-adiabatic couplings in your set of equations?
And this term is a J and K coupling between the J state and the next in the time step with the K time step, and is giving us this coupling.
So instead of placing time as a parameter of orbital, you just put operator of time derivative between them.
Yeah.
Okay.
So we can read out the T if we could substitute this equation here. So in our methodology, we divided this whole thing as a 3-step. So it would be very convenient to discuss about in the first step, and a little bit slow one. And Daniel's discuss about this one. First, we need to get the optimal geometry, and I didn't show the Inca file because everyone already saw that one. And then we need to create a geometry at the room temperature, the higher temperature, like usually we do at 300 degree Kelvin. And then at the higher temperature, we can apply the molecular dynamics, and then we will get the trajectory at the certain time step, whatever you want. And important thing is when you're getting we are doing the adiabatic trajectory, we need to define the port. We need to keep the portim at a reasonable number. Is based on the system, what type of atom it is, and usually we get some idea from the IR spectra of the similar metals, then we can. And this portim supposed to be smaller than the lifetime of oscillation of IR, or highest number of frequency. We need to get that one, and this period should be the smaller than that. I mean the portim. And then, as Landon told that, we got the all geometry from the adiabatic trajectory from the step 1. And then in the step 1, I use the exact curve. I use the out curve. In exact curve is to me exact curve is easier because exact curve define the cell, and then is define the all coordinate at the every time step. So I can just slice down at the time a certain line because it's have a uniform format, and then put it on the one file name as a postcard file, P file. So P file is nothing but it's just a postcard file for at that time, at that moment of the time step. And then we create the defined directory. We usually say the P directory because if we create the 1000 or 2000 trajectory, it's not possible to run the whole things at the one time. So rather than running in one time step, we divided that by 50 or based on where I'm doing the calculations, like 50 or 100. And then, but one thing we already discussed on the answer questions on the random things, we need to overlap some step in between the in all step, because as you know, the initial web car is not a very precise one. If we do that, then we can exclude the first 5 steps and then take next one. It will give you the nice continuity. And then actually we do this time step by calling, in our method by calling one script. This is a Perl script. So this Perl script is actually nothing but this Perl script call all other required script. This script doesn't do any calculation, it just calls the script. And I do all this calculation in the NARSC, and so not NARSC, here in Thunder. I had some problem to call the bus directly from the Perl script. So instead I run a bash script and then Perl call that bash script to run the bus. Landon already showed the cycle, so it's kind of almost similar cycle.
Yeah, but are you planning to explain numerical parameters?
Yeah, I'm going to this one here.
Because
so
it
this
looks
one,
like 1, 2, 3, 4, 5,
yeah.
6 numerical.
So
parameters.
in this parameter, one is calling the for first is calling the for bus, running all calculations, and then take the single point calculations, create the web curve, and get the energy, all of them. And then these two parameters, first two parameters are actually number of bands from where to where. So we want to calculate a band of energy, not the whole of the band. So this indicating that the lowest band is 141 and highest band, highest LUMO band is 540. So the 200, 200, total 400. And thing is, and in this script, they have another script actually, the formatting energy.
Your HOMO is 340?
Yeah, 340. And 341 is the LUMO orbital. And then it will call another bash script. This is just formatting the energy. So this and then it's numbering the band according to, starting from the 1. That means 141th band is first band in this file. So this energy file contains the energy of the 400 bands, 200 LUMO, 200 HOMO. So, and the first band is a 1 to 400. And then next thing is to calculate the oscillation strength. So we have a similar script, and then it calculate the oscillation strength at each moment of time from the web curve, and that web curve and the previous web curve old and web curve. One thing is defined is our calculation. You will see the web curve new. Actually, it's calculated. It's copy the old web curve to the web curve old, and right present web curve as a web curve new, and then get the oscillation strength between web curve old and web curve new. Because we did not move the web curve, because this web curve is going to be used maybe in the next calculation. It will increase the speed of the system. And then we also calculate the coupling. And the number naming of the thing is important, is that they are real with the number of time step, and this one is OS on the time step. And then after running this script in one orbital, okay, no, there are another thing is, so suppose like here, so it's getting the band from this number, so this first two argument is the number, and the next two is the script is running from this time step to this time step. So in my calculations, I get the period with the 50 time step, so this 50 on here. And these two things actually the number of processor per nodes, and this is the total number of processor per nodes. So I run this file, this example in the Thunder in our cluster. We have a 20 core in each node, and then I use the 2 nodes. Total is a total nodes. So if I use the different system, we need to change this number too. And this is important because because when is run the bus, we need to ask a bus how many core it should use to calculate each band. Because there are some memory issues and other issues, and there are optimal number too. So this number is used for calculating the N core number and other things. So these are six argument here. So for if anybody is going to use the wasp, in the Thunder, in these calculations we didn't call the wasp directly from here. Rather than just one thing, remember, I just give all informations, I mean physical PBS informations, and then put this script, and then all module loading and everything is listed on the another different script, and is called during the running this part script. So after the step 2, we will get a real file. That's real file means is coupling. We will get an OS file. That OS file is for oscillation strength, and we will get energy file. This energy file is running the the energy of the 400 bands of these 50 steps is written in this energy file. So one thing is, after the completion of the step 2, we will get a number of bands, number of directory, like 10. Suppose like if we get a 10p directory, we will get a 10 energy file, and that 10 energy file, and I also told you that we have some overlapping between the 5 steps. So that means after that step 2, we need to create a complete energy file, which will have all energy band, and we need to exclude the first 5 lines. 5 line means for energy from the 5 time step, and then need to run get this remaining 45 time step. It should concatenate in the new file and get a big energy file. So all of these streaming things actually we call as a pre-step 3. That means just processing all data to start to getting ready for step 3. And this manual actually solely written for using myself, so maybe you will get a lot of grammatical or other errors. It just I read this one just to understand myself. I put it here. So what I'm doing, just copy the all real file from the all directories and OS file, and I have a own Python script to copy this from go to each directory and copy this file. But during this copy, we need to keep in mind we are excluding the first 5 OS file, first 5 real file, and first 5 energy lines. And then to run the step 3, we need the 2 input file. That input file, suppose like I should give you the example. Give an example of this. What is the file it is actually? So, but this from st to _st is just a one name, because we don't need to. We need to keep this name because following is script to read the file according to this name. So here it will give information about how many band we are going to calculate, and what's the initial, and what's the final band, and what's the homo, and what's the low, these kind of things. And another file, this input file, this also contain the all parameter. This parameter is contain like what type of transition we are going to consider. Suppose like transition is a symmetric transition. Symmetric means the homo energy, electron energy and hole energy either equal or close to the equal. Then we consider those transition is like symmetric transitions or asymmetric transitions. And then it also contains information about what would be the threshold value to calculate the symmetry or to calculate the transition energy, because it's very unusual. Yeah, it's very hard to get the information from. Yeah.
Can I give a just brief comment? Maybe there will be a question. So, in previous approach, the initial condition for electron dynamics was determined by the parameters I, E, and IH for initial orbitals of electron and hole, once and forever. In the approach that Jebet is explaining, there are steps to take into account the average over several possible initial conditions. So there is a subsequent run of the electron dynamics with different initial conditions approximately giving the same excitation energy, and then adding them together and looking for ensemble average. So it is what Javid was explaining.
Was that why the first 5 steps are skipped in like all of your calculations? I guess I can't remember why you don't want to include the first 5 steps.
The thing of his pre-step 3,
yeah.
In Redfield approach, there is no pre-step 3. You just set up initial electron and initial hole.
Mm.
In this surface hopping approach, you do create set of initial conditions over which you later perform an average. And the image that Javid is drawing will be explanation of how this distribution ensemble of initial conditions is created. So please keep going.
Yeah, so this one is kind of like, suppose like in your system there are a lot of different types of transition, but you cannot, you will get that as information from oscillation strength. But for this calculation, you don't need to consider the all transition. There are some dark transition, some bright transition, and also they have energy also on big effects. So before in our system, first we try to focus on some energy, energy range. We will focus on those transition only. Suppose like in these calculations, in these things, suppose if you get this example, this exciting from the close to the frontal orbital to the very high energy too. But in this type of transition is from the deep hole to the close to the frontal orbital. So this, what type of transition is happening is also system dependent. What is the band density and all other parameters here. So to differentiate the different nature of the transition, we can explicitly define the initial conditions, which transition we are considering for the step 3. So all this information will be in this file. Suppose like as I said, suppose for example this is the asymmetric hole, or hot hole transitions. This type of transition we use to say hot, this one is a hot electron, this one is a hot hole, because this hole energy is higher than electron energy. And this one is almost symmetric transitions, because hole and electron transition are almost similar. As same as this one, but this one is close in the low energy, close to the here, but this exciton energy is higher than this one. So there are a bunch of different types of transition, and we will define these all parameter on this file.
So all these transitions are included in the initial conditions?
Not all.
It depends how
you define.
You can just choose with respect to the energy, and then all of them will energy and oscillator strengths, of course, right? But then you don't differentiate between which symmetric, asymmetric, hot hole, hot electron are involved. Or you can really kind of include only this or that.
Your call will be disconnected.
So kind of it gives you additional constraint to put into your initial conditions.
So you can
Sorry, what is it that makes it a hot electron or a hot hole?
Sorry, what?
Like, what is it that makes something like a hot electron or a hot hole? Like, what is it?
This means suppose like if electron is exciting from here to here, so it's leaving a positive charge here, right?
Yeah.
I mean C2 positive particle. It's not a particle, but it's a
C2
particle. And
like
then
hole has smallest energy, electron has the highest energy.
So,
right? That's what
Wait,
we call
say
hot
that
electron.
again?
Hot electron, when you excite electron at higher energy states.
Okay. So like from near the HOMO, or?
So if this whole energy, like, what does it initially do? If this excited electron, then it reduces to the frontal orbital.
It's easy to explain. Start with a symmetric case.
Okay, suppose
and define like what we define: energy of electron, energy of hole, right?
Okay, suppose like here, this is the whole energy, and this energy is.
So you're talking about the gap between the two levels?
Yeah,
your energy that you're talking about?
It's not that actual gap, it's just a difference in electronic levels in the valence band. For holes, right?
But it's the difference
where you
between
excite
the energies.
to the HOMA,
Yeah.
right? And then the same you can define from luma to where you excite your electron.
Okay, so it is just basically the distance between HOMO and wherever it started, and then LUMO and wherever
Exactly.
it ended.
Yeah,
Okay.
And then you can imagine, you can make it really completely symmetric, like your energy of both of carriers would be exactly the same,
Yeah.
with whatever, 3 electron volts, whatever your energy is defined. Or you can really have your hole being already in an age of the valence band, almost no energy. Doesn't have really too much freedom to relax, it's already there, right?
Yeah.
But your electron is still very high, so it has a lot of possibilities to return back to the low state during relaxation. Or backward, you can put electron very close to LUMA and hole can be really far away. And this is what we call hot electron, hot hole.
Yeah, we are saying this energy is for electron energy because what's happening here, if after excitation this electron will come here and hole is come here, and then there will be recombination, be radiative or non-radiative. So that means these electrons can travel this much energy only. So that's why we think that this is a base energy for electrons. So you can say this is the electron energy and this is the hole energy.
Okay.
Make sense?
And it depends on the system, right?
Yeah.
When you can, like, why we use it, because you can really use this as a tool to identify the properties, because they based on the symmetry, well, of course, on the symmetry of your lattice, if you're talking about solids, and it's also on the symmetry of your, or kind of symmetry of the wave functions, right? And density of states for these transitions. So it depends on the system, and in one cases you can see, or depends on the energy weighting side. In one cases you can clearly hot hole or hot electrons.
Okay.
In some cases it's completely a mixture, and then of course you don't need to differentiate between them.
Okay. So in that far left arrow that you have pointing up there, that would be a hot electron or a hot hole. The
this
far
one?
left.
Left.
Oh, sorry, left.
Hot electron.
I would say this is a hot electron.
Okay.
Because the electron energy is higher than hole
Yeah.
energy.
Yeah. I'm just trying to make sure that I'm like interpreting this
It
correctly.
is
I guess.
it's kind of like, it's not a conventional term, but our term, it's not a super conventional term.
Yeah.
Established conventional.
Well, right. Yeah. I just want to make sure. That
But
I'm
this is a
actually
common
understanding
term in this kind of
this being
discussion, like
do.
using the hot hole and hot
But
electrons.
this picture is also very convenient when people talk about carrier multiplication, right?
Like
kind of going through the
multiple exciton
multiple
generation?
exciton.
Okay.
Yeah. So it goes through the mechanism through the Auger processes.
Yeah.
So it means like if you have a hot electron, and suppose your energy is at least 2 band gaps.
Yeah. Then it can
So
relax
you can lose,
still in the
you
conduction
can lose this
band.
energy of electron,
Yeah.
right? Which can be given to the electron from another electron
Yeah.
from the edge of the valence band, which will push this electron to the LUMA, and now you have 2 carriers instead of 1, right? So again, this is easy, or maybe can't say.
Yeah, in this case it's easy because
Easy to use and differentiate
Yeah.
between different types of excitations.
Okay.
like if you have a photon which energy is twice as a band gap, so by using that photon you can excite from here, or from the front orbital. Which process will give you the more possibility to create the multi-exciton generation? Because if you have a hot electron energy which is equivalent to, which is enough to get another excited another electron from HOMO to LUMO, then you will get a
Yeah.
multi-excitons.
But for symmetric case,
For symmetric case,
you need much
maybe
higher
no.
energy to
Yeah.
have the same thing.
Because your energy is divided half to the hole, half to the electron. So ultimately,
Or you need really to
Yeah.
have a very strong coupling between electron and
Mhm.
hole, so they can move simultaneously
Yeah,
and
simultaneously.
release this energy
Right,
as well, right? But then this possible only when they're really very strongly correlated through the Coulomb interaction.
and
But
because
somehow
of-
we
yeah.
went to the physics instead of technical skills. And BT should punish us.
And because of the multi-exciton generation, we define this energy based on the band gap.
Okay.
Plus 2 band gap or 3 band gap window.
Yeah,
So
yeah,
we
that makes
always
sense.
select the energy window by times of another band gap, and so it will, instead of giving an absolute number,
How many slides you still have?
just a couple of slides. We're already on pre-step 3. So yeah, and then if we ready with these 2 input parameter file, and then we need to run this script. This script is just calculate the coupling and then give, not coupling, initial excitation from this all information, coupling information and voice informations. Then you will get the number of file here. This I just read the all file, and you will get the DOS in electron and hole and icon dat. Icon dat is contain the all initial transitions. Which band?
Like
which
constants for initial condition.
Initial condition, yeah.
And E and H stays for the electrons.
Yeah, E for electrons and hole for H for hole. And the numbering is important here because then after the getting this, after the second step, we change the numbering because now it started from the 1 to 400. So 1 to 200 means is a LUMU, and 2 to 200, 200 to 400 means, sorry, 1 to 99 is LUMU.
Yeah.
200 to the remaining one is LUMU. And if you look on the icon dat, this icon dat also, they have another thing is, and we want to relax the electrons to this band, to suppose like this band, and we want to relax hole to this band, to this band. So if you look on the directions, this direction is actually opposite directions. So this is the, and this energy is lower energy compared to this band energy. So that means we are relaxing the hole from the lower energy to the higher energy. So in our code, work should go to the electrons or particle, not electron or hole as a particle, go to the lower energy. So because of that, when we run this script, is create another energy file for hole where the energy is
Negative.
multiplied by -1.
Okay, yeah.
So now you are getting the opposite direction, but is making your low energy. And numbering also change according to that way. So if you look on this one hole, you will see that is exciting from the close to the 200, but this one in the electron is excited.
How we numbering it? Like you go in HOMO is number 1 then, right?
The HOMO is started from the number here to here, and here,
LUMA starts from number 1.
LUMA number 1.
So it goes from lowest to
Good
highest all
message.
the time, going 1 to whatever.
Yeah.
Wait, LUMO is number 1?
Oh, because we split that.
It is because of split the energy.
Oh,
Yeah.
Like
okay.
technically you prepare input files for electrons and input files for holes.
Yeah.
And then when you run it's a pre-step, right? When he runs step 3 for the actual dynamics using surface hopping, then you can run them simultaneously on the different directories, one for electrons, one for holes.
Yeah.
So
Yeah.
don't talk with each other.
Okay.
So
your code's also doing pretty much the
Yeah.
same thing.
But you're going to have two different, like 1 to 100, 1 to 100 or whatever.
So we need to run the step 3 separately for electrons and holes.
Yeah.
So what I do, we create a one directory for electrons, we run this all of these things, and we got all parameters file for electron and hole. Then we create another file, another directory with the hole, and then move everything there. And then we rename this file. Or if we call in electron directory, you need to rename this file electrons, and hole you need to rename the other file. And for in case of energy, because this energy formatted by for hole, you need to change this energy file to the energy, and you can use the original file for electrons. It doesn't matter this. And they have another file. If you want to look on the orbital band number, they have another file is give you the information about the which old number and new number. Then it will help you to figure it out. Now time to run the step 3. Step 3, if we need to run this script. This script do all these calculations. Actually, this keyword for running for a photon, but this one is a Linux command. It will let you run this in the background, so you don't need to keep your shell open for all times. So same thing, actually same script will work for the Thunder too. I can use excuse me on the Thunder. So I already told about this information. And after the step 3, we will get all information, result, and then we need to do some post-processing things. This is known as a post-step 3, or I just running the step 3. And first one is to need to run this script. This script will run on the SS state file. This is containing the all coupling information here. And then after this one, you will get average surface hopping, and then you will get this this file with probability for normalized probability or other information. But we need to.
What's the difference between them again? These two files.
Actually, I didn't look on this file. This one is the average surface hopping, but this one is the.
I think it tells you statistics, right? So it means it probably has information
average
on,
one,
not without average. So it's kind of put is probably like you can
Average
really get a distribution for at which energy windows when you go step by step you get in this the most effective transitions. Let's say, for example, you have a big splitting between electronic levels, right? So let's say at high energy you have all your splitting is very small. But when you go close to gap, you might have a few states which will be splitted very much, like in molecules, almost. And for nanostructures, this is very possible. Our lumens typically shifted, they split it from the main band. So then, because of very strong mismatch between energies, right? So you expect that you might have very different times or probabilities, which dictating your times of the jump, highest versus when you come in closer to the edge, right? And then kind of you can really get into more details instead of averaging everything. You can really look on it kind of carefully for all cases and look on a distribution. Might be useful.
And then we need to run another script. This one I did not show. So, excuse me. So this script will do like something. As you saw the population, if you want to write the population, how population is relaxing to the time and energy. So we do the population and does these things for electrons and holes separately. And it will run a rate. Sometimes our methods sometimes work and some other system didn't work. That's why I asked questions on how we calculate the rate in his methodology. And
when you say it doesn't work, it's not like it doesn't work and give you errors. It's always calculating the files. But when you plot your files, you see like all kind of oscillations.
It's very hard to
It's not showing nice, beautiful functions.
Hard to translate to any result. I mean, physical result. It's maybe because the relaxation is not following the single state. First order relaxation. So if you get the first order relaxations, you will get a nice exponential curve, exponential fitting. So it's maybe because of there are some internal excitations and then relaxations to the or it's maybe related to the multiple state. A population is like 0.5, 0.5, 0.2, 0.3. So in that case, you will get.
You don't finish in your relaxation at the end.
I forget that term is like higher order relaxations. If that relaxation is related to the relaxing from the multiple state, not from the one state. So in that case, it's very hard to define your rate by exponentially, or it's going to by exponentially. And there was some like my own script to get this plotting this one. I was trying to show you
You're not plotting with origin. You making your own script and then.
Origin means because it's written in separately, and also energy window is very long, so you need to spend a lot of time to get a one matrix put in one things. So rather than I write a Python script, is just get that information from the electrons and holes and make a single matrix and just put it in origin.
And again, your DOS pop file includes like. It's multiply your dose at this moment of time to the population at that moment of time, average population, I guess, right? But kind of with the same time interval as you were running through the dynamics, let's say 1 femtosecond interval, right? So it means you have 1,000 steps, you will have 1,000 points in this file, right? for the time
For
scale.
the time, yeah.
And you saying that you're reducing this, like you're taking not every femtosecond, but every fifth or something like this, or how you reduce the size of the file?
Size means this file is written for whole energy window.
No.
So
like you're not taking
is it
less.
zero? Yeah.
You're not taking less kind of snapshots from your trajectory. You're just playing with
I mean,
energy bands.
Yeah, formatting these things. Yeah, it doesn't do anything. It's just a formatting and compiling the two files, because we will get a one electron relaxation from one directory, whole relaxation from one directory. So if you plot separately, you will get whole electrons, and another figure you will get just electrons. So if you want to plot in origin, you need to do some tuning and putting on the one matrix. So in this case, it's doing these things, nothing very important. And this script, I have another script to do the average electron and hole. If you remember in Aaron's, in Aaron's figure, you see the one line is showing
like
you
exciton instead of electron and holes.
In both cases, yeah, it gives you the average electron energy and average hole energy. I can show you the figure. Oops, I don't have this one.
Well,
So that's the
Osamus is already disconnected, but we are still on the recording, so we can.
So there's the for rates calculations to run the another script, and it's for exciton relaxation. So what do you need? We need the rates file from the electrons and the hole, and put it in the one separate directory, and also out file, and then you do this all calculations. And that's all about our third step 3. And there are some other related calculations like plotting the absorption spectra based on separate. This is not related to the surface process.
Okay, thanks. Java. Any questions to the speaker?
I should include some figure too plotted, but I didn't do this one.
We will repeat same things maybe next year.
No, I mean if I show the figure, then it will make more sense to what is going on there.
Well, if there are no more questions, let's thank all the speakers once again. Let's hope that this meeting will be helpful in using practical skills for analyzing your models through electron dynamics and